If electrical troubleshooting has ever been a frustrating experience for you, well, join the club. A lot of technicians I've worked with don't like electrical troubleshooting. Electrical ROs used to make me cringe. I mean, what a time drain. I'd eventually fix the bike, on a good day, but I had my fill of those ROs, and so did my customers. After a few disappointing paychecks due to comebacks and lost hours, I decided to start from scratch. I found that understanding the basics helped. It took a while, but the more I understood electricity, the more everything came together, and the easier it became to troubleshoot electrical problems. I'd like to pass on the information that turned my troubleshooting around. By the end of this program, you will be able to define electricity and describe its three necessary conditions, identify the function of conductors, insulators, and semiconductors, describe the two ways electricity is supplied on a motorcycle, and identify 4 types of alternators. Electricity has always been somewhat mysterious because, well, it's invisible. But you can learn a lot about it by observing its effects. Electricity is basically the flow of electrons from a source through a conductor, completing a circuit back to the source. Electrons are one of the 3 components of an atom, which is the basic building block of nature. Electrons have a negative charge. The other components of an atom are protons, which are positively charged, and neutrons, which have no charge. Normally, an atom has an equal number of positively charged protons and negatively charged electrons, and is said to be in balance. However, under certain conditions, an atom will lose or gain an electron, making the atom unbalanced and creating free electrons. We've learned to control the movement of these free electrons in order to generate electricity. To generate electricity, 3 conditions must be present. 1, there must be free electrons available to move from atom to atom. 2, there must be a difference in charge. And 3, there has to be a complete circuit. Let's take a look at these 3 requirements in more detail. First, in order to have free electrons, you must have material that gives up or receives free electrons easily. These materials are called conductors. Copper, for instance, is made of atoms that easily release or gain an extra electron. Inside the battery, a chemical process causes the atoms with the extra electron to move to the negative plates. The atoms that have lost an electron move to the positive plates. Since the electrons and atoms want to be in balance, the difference between the positive charge on one side of the battery and the negative charge on the other side of the battery creates a potential difference. This difference in charge is the force known as voltage. So there has to be voltage in order to have electricity. This leads us to the 3rd condition needed for electricity to flow: a complete circuit. A complete circuit is simply a path through which free electrons can flow toward the positively charged atoms. If the negative and positive sides of the battery are connected with a good conductor, such as a copper wire, the potential difference or voltage will cause the electrons to flow from the negative side of the battery to the positive. This is current flow, or more correctly, electron flow. But wait, Haven't we always been taught that current flows from positive to negative? Well, yes, we have. When scientists began formulating theories of electricity, the existence of protons, neutrons, and electrons was unknown. The scientists simply assumed electricity flowed from positive to negative. This is called the conventional flow theory, and we know today that it is incorrect. Electricity actually flows from negative to positive, which is called the electron theory. Though we still use conventional flow from positive to negative in service manuals and electrical troubleshooting manuals. In reality, the theoretical direction of electrical flow has no impact on your troubleshooting. In fact, the main thing to remember is not which direction current flows, but simply that it flows. Now, let's look at why some materials are better electrical conductors than others. And what we'll find is that it all comes down to resistance. In fact, the ability of a material to conduct electricity is a measure of resistance. How well a material conducts electricity can be broken into three categories. First, materials that conduct electricity easily. These are called conductors. Second are materials that do not conduct electricity. They are called insulators. And a third category that are neither good conductors nor good insulators are called semiconductors. Let's start with conductors. A conductor is a material whose atoms allow electrons to move easily from one atom to the next. A conductor is simply a material whose atoms gain or lose electrons easily, so they promote current flow. When voltage is applied to a good conductor, the free electrons move easily. Copper is a good and commonly used conductor. Gold and silver are excellent conductors, but they're obviously too expensive to use in motorcycle wiring. All conductors have some resistance, and the amount of resistance is influenced by factors such as the diameter, length, and temperature of the conductor. In copper wire, as the diameter of the conductor decreases, resistance to electron flow increases. Resistance also increases as the length of the wire increases or the temperature increases. So, circuits that carry a lot of current, like the starter circuit, usually have large wires. On the other hand, circuits that carry small amounts of current, like a taillight circuit, have smaller wires. Even when voltage is applied, the electrons of the insulator are held too tightly to be moved. That's why no current can flow through it. An insulator is like the plastic coating around this wire. It offers a high resistance to electrical flow. This helps keep the electrons flowing only in the desired path. There are many types of insulators used on a motorcycle, such as plastic resin, vinyl, and rubber. They all prevent current flow. This brings us to semiconductors. When it comes to conducting electricity, semiconductors are an in-between material. They offer better electrical conductivity than insulators, but less than a good conductor like copper. Semiconductors are important because scientists have found ways to alter them so that they will conduct electricity under some conditions but not under others. Silicon is an example of a semiconductor. A diode is a common motorcycle application of a semiconductor. Think of it as kind of an electronic one-way valve. It will conduct electricity in one direction, but not the other. You'll find other semiconductors in motorcycle electrical systems. For example, transistors act as solid-state relays, while thyristors are solid-state switches. Electronic control units found in many electrical systems are made up of hundreds of these semiconductors. So, we have learned what makes a good conductor, insulator, and semiconductor. Now that we know what electricity is, the next question becomes, how is it supplied? The two sources used to supply electrical energy on a motorcycle are the battery and the alternator. Chemical action is used to produce electricity in a battery, and magnetic induction is used in an alternator. Let's start with the battery. In each cell of a motorcycle battery, there are a number of dissimilar metal plates that are submerged in an acid solution. The acid solution, or electrolyte, reacts with the material on one plate more than the other. The more reactive material loses electrons and becomes positively charged. The less reactive material gains electrons and becomes negatively charged. The difference in these positive and negative charges generates a potential difference, or voltage, causing current to flow through a circuit. The positive and negative plates are alternately arranged in cells. The size and number of plates in each cell determines the battery's capacity. A motorcycle battery has either 3 or 6 cells. This battery has 6 cells that each produce approximately 2 volts. The cells are connected together in series, so the total voltage of the battery is about 12 volts. As the battery is used, the composition of its plates changes, and its acid content weakens to a point where the battery is discharged. However, if electrical current is forced back into the battery, the plates will return to their original composition, and the acid will return to its original strength. How do we get electrical current back into a discharged battery? From an alternator. The alternator uses magnetism to create electricity. Magnetism is a physical phenomenon of nature. Put iron filings near a permanent magnet and watch them move. This movement is caused by the magnetic field surrounding the magnet. The larger and stronger the magnet, the larger and stronger the magnetic field. Spin that same magnet near a coil of wire, and electricity will be generated in the wire. In practical applications, such as a motorcycle alternator, a series of magnets is positioned in a rotating flywheel surrounding a coil of wire. Or in some cases, within coils of wire to generate electricity more efficiently. Several factors influence the generation of electricity in this manner, including the strength of the magnet, the number of windings in the coil of wire, the closeness of the magnets to the coil, and the speed of the magnetic field's movement through the coil. Now, how does an alternator work? Well, inside an alternator is a coil of wire called the stator. This stator coil is surrounded by a rotor which has magnets in it. The rotor turns with the engine's crankshaft. As the rotor turns, its magnetic field moves across the stationary coils of wire, thereby creating voltage. The faster the engine turns, the more voltage is created. This is obviously an oversimplification of the process. Certain controls are needed to make this process usable in a motorcycle. For example, the alternator produces alternating current, but the motorcycle's battery requires direct current. So the alternator circuit is equipped with diodes that allow current to flow in only one direction, converting AC voltage into DC voltage. This conversion is called rectification, and there are a number of ways to produce and rectify AC voltage into DC voltage needed for the battery. The simplest is called half-wave rectification. With this system, a single diode is connected between the alternator and the battery. It allows one half of the output to pass to the battery, but not the other half, meaning the system only makes use of half of the alternator's output. This is not a very efficient system, but it does provide sufficient electricity for some of the smaller Honda motorcycles and scooters. A more efficient design is called full-wave rectification, and it uses the entire AC waveform instead of just half of it. The result is a system that can use all of the electricity produced by the alternator. 4 diodes are grouped into a bridge circuit. Each time the alternator's current reverses, the rectifier diodes provide a path to the battery's positive terminal, so no current is lost or wasted. You'll see this type of system on some Honda motorcycles built before 1992. Most current Honda motorcycles and ATVs use what's called a 3-phase alternator with a permanent magnet rotor. While roughly the same size and weight as full-wave type alternators, the 3-phase design is far more efficient. It utilizes a 3-phase stator and 6 diodes instead of 4. It's referred to as 3-phase because it has 3 single windings spaced so that the voltage induced in each winding is 120 degrees apart. Think of it as 3 full-wave systems combined into one. The 4th and final alternator design uses an electromagnetic field coil in place of a permanent magnet. A magnetic field is also created when current flows through a conductor, such as a copper wire. The greater the current flow through the wire, the stronger the magnetic field. If the wire is wrapped around an iron core, the iron core concentrates the magnetic lines of force. If the magnetic field is moved back and forth across a wire, it will generate voltage in the wire. This is called electromagnetic induction. A controlled amount of electricity is sent to the field coil, which induces a magnetic field in the rotor. This system is found in a small number of Honda models. An important difference between alternators using permanent magnets and those using a field coil is the motorcycle using the system with the permanent magnets can be started even if the battery is dead. Now, let's review what we've learned in this program. Electricity is the movement of free electrons from atom to atom. For electricity to flow, 3 conditions must be met. 1. There must be free electrons. 2. There must be a difference in charge or voltage. And 3. There must be a complete circuit. Certain materials promote or inhibit the flow of electricity. Conductors allow efficient current flow. Insulators prevent current flow. And semiconductors conduct electricity under certain conditions, but not under others. The 2 sources used to supply electricity on a motorcycle are the battery and the alternator. The battery produces electricity through a chemical reaction. The charging system employs an alternator which produces electricity using magnetic induction. This magnetic induction is provided in one of 2 ways, through permanent magnets or electromagnets. The electricity produced by the alternator must be rectified or converted from alternating current to direct current. There are three methods of producing and rectifying the electricity in Honda alternators: half wave, full wave, and three phase. For more information on everything you've just seen in this program, be sure to refer to your resource guide entitled Electrical Principles. Understanding how electricity flows and is supplied is crucial to quick, effective troubleshooting. As I said earlier, the more you know about electricity, the more everything will come together. You'll have fewer comebacks, healthier paychecks, and more satisfied customers. And isn't that what we all want?